My name is Venkat Anantharam. I might know some of you, but if you don't, I'm on the faculty in EECS. So Girija asked me to give one of the guest lectures this week. So I'm going to give you a guest lecture on what's called semi-definite programming. The short for that is SDP. I'm going to be using slides, and the slides will be available on the on your website, whatever, for the course. So the talk structure of the talk is going to be to define this class of optimization problems called semi-definite programs. They're also convex optimization problems. They include as special cases all the problems that you've seen so far: linear programs, quadratic programs, QC, QPs, SOCPs. I'm assuming you've seen all of these, right? So they're all special cases of semi-definite programs. Semi-definite programs are extremely important for applications and also in computer science, it turns out. There's a lot of active research on trying to understand approximation algorithms for various combinatorial problems, complexity questions, where semi-definite programs play a very big role. There's also a theory of duality for semi-definite programs. You've seen duality in optimization. The kind of duality in semi-definite programs is better thought of as something called conic duality. I'm going to define what that means. It involves a notion of a subset of Euclidean space called a cone. That's a formal definition. So we are going to start with that. And what you see in this first slide is a definition of a cone. So a cone is a subset capital K of, say, n-dimensional Euclidean space. Before defining, the second line defines the cone. So the property you want is that any vector in K, I am not sure if I have a pointer actually, that might or might not help. Well, I have a computer, so can you see the hand? Oh, great, okay. So for any vector x, so Girija has the habit of using vector notation on top of these x's, and I have the habit of not doing that. So I've co-taught the course with her in the past where we use the vector notation. When I teach it myself, I don't use it. So you're going to see a mix of both conventions. So here x is a vector in X. We need the property that if you scale it by any non-negative number alpha, you should still be in the cone. So the idea is it's a subset where if you're sitting in a subset and here's the origin, and you sort of go along a line, scale it by non-negative number. So you go along a half ray, so to speak, or half line, which goes from the origin to that point. That entire line has to be in the set. That's the idea. So you can see the pictures to get some intuition for that. Now, in contrast to these half lines, there is a notion of a line. A line is a subset which is defined by some vector in Rn, where all multiples of the vector lie in the line. So here you have a vector. You can go both with negative and positive coefficients. That's called a line. Basic example of a cone would be just a subspace. In fact, a subspace is comprised of lines, right? Because if you have any vector in a subspace, you can multiply it by both a positive or negative coefficient. Either a negative or a positive coefficient, you'll still be in the subspace. But the notion of a cone is more associated with positivity. You want to be multiplying only with positive coefficients. So mostly we're in this cone business, we are interested in some terminology. This is not so important for us, but since I'm introducing cones, you might as well see this terminology. A cone is called pointed if it contains no lines. So for instance, the subspace will not be a pointed cone because it has lines. It's just a word. You don't have to worry about it. It's not important for us later, but you should just know the definition. A cone is called convex if it's a convex set. You're supposed to know what a convex set is. You've studied it a lot in this course. A cone is called closed if it's a closed set. A closed set is a set where if you take limits of points in the set, sequence of points in the set, you continue to lie in the set. So that would be what it means for a cone to be closed. And a cone is called solid if it has a non-empty interior. That is, you can find some point inside the cone so that if you take a small ball around that point, you're still in the cone. These are just some words, okay? They're not important for the rest of the course. I'm just introducing them because I'm introducing cones. If you want to understand cones, these are useful words. Let's start out by understanding by looking at some examples. So how do I go? What do I do here? So here's a couple of examples. So let's look at the example on the left. that cone is clearly pointed because it doesn't contain any lines. It's also a convex set. And if it happens to be closed, so whether it's closed or not depends on whether the boundaries, so to speak, are in the cone. That's not very apparent from the figure. Then it would be called what's called a proper cone. So proper cone is one which is pointed, closed, convex, and solid. A cone is clearly solid because it seems to have an interior, right? It's in three-dimensional space. The example on the right is pointed because it doesn't contain lines. It's also clearly a closed set. But it's not convex, as you can see from the figure, and it doesn't seem to have an interior in two-dimensional space, so it's not solid. Just to give you an idea what these definitions are. You'll have the slides, you can look at them more carefully later on. So in the theory of cones, the notion of a proper cone is what people are mostly interested in. And we are going to be discussing the cone of positive semi-definite matrices. That turns out to be a proper cone. And that's what's relevant to semi-definite programming. So that's what I'm going to talk about. Okay, what happens? Okay, great. Now, I told you that there's a theory of duality in cones. So you've already seen various kinds of duality. You've seen duality presumably in convex programming through Lagrangian duality. In linear algebra, you've seen the notion of duality through things like transposes, orthogonal complements, things of that sort. So you know that duality plays a great role in optimization theory. When you're dealing with the optimization theory of conic problems, there's a kind of duality that is compatible with all these other dualities, which is called conic duality. And the process of creating a conic dual is to start with a cone. So here I have my cone capital K. And I can define a new object, K star, which is called the dual of K. K star consists of all the vectors which have got a non-negative inner product with every single vector in K. So a vector y will be eligible to be in K star if and only if its inner product with every x in K is non-negative. It's easy to see that K star is a cone because if you scale any y that has this property by a non-negative coefficient, it will continue to have this property. So K star is also a cone. It's called the dual cone of K. So one baby example is if you start with a subspace in Rn, call it V, and you look at all the vectors that have non-negative inner product with every vector in V, then that's basically the orthogonal complement. Because the point is you can scale a vector by either positive or negative coefficients. So if you basically will end up having to have this inner product to be 0. Because it has to be non-negative, so it better be 0. So if you have an x if suppose you have a y which has a non-negative inner product with x, and it also needs to have a non-negative inner product with minus x, because you're dealing with a subspace, you're trying to form the dual of a subspace, it better have 0 inner product. Right? So this is a baby case which might be slightly atypical, but this is an example of what it means to form a dual. Now it can be shown that if you take the dual of the dual, that is you start with the cone K, you take its dual K star, and you take the dual of K star, so that's K double star, then you basically end up getting the closure of the convex hull of K. I'm not going to prove that, but you can think about it. Question?
Sorry, when you say the closure of a convex hull, what exactly does the closure mean?
Closure means you take all the limit points of sequences in the set. So if you take the open interval, for instance, which is not a cone, and you close it, you'll get the closed interval of some sort, closed unit intervals, let's say.
Okay.
You're just taking all the limit points. That's what closure means.
So isn't the convex hull closed by definition?
No, it's not, because if you take a unit, let's say you take the open unit interval, it's a convex set, but it's not closed, because 0 and 1 are not in the set.
Oh, okay.
Yeah. You can have sets that are convex but are not closed. Okay, these are not important notions, so don't get worried if you're sort of also on the same page and don't follow this terminology very clearly. This is just to give you some basic facts about cones. It's not going to be that important in what I'm going to say in the rest of the lecture. But the answer to your question is by example. Convexity does not imply that limit points lie in the set. Think of the open interval. So if you take the open unit interval, so if you take a set K, you form its dual again, then one can show that you get the closure of the convex hull of K. Now all this is just to give you some terminology relevant to cones. The object of interest to us is the set of positive semi-definite matrices, for which I am using the notation S sup n for n by n symmetric matrices, and the plus underneath means that they are required to be positive semi-definite. I hope that's consistent with the notation in this course. Now it's clear that this is a cone. If I give you a positive semi-definite matrix, so this basically is a subset of the set of n by n matrices, which is a vector space, right? You can think of it as like r to the n squared or something. So it's a subset of r to the n cross n, or r to the n squared, right? Now if I take a positive semi-definite matrix and I scale it by a non-negative coefficient, I will still get a positive semi-definite matrix. I hope that's clear. So this set is a cone, and it turns out that this set is a proper cone. You can show that it's closed, it's pointed, it's solid, and so it's, you know, it has all the properties that we wanted. So it will be a proper cone. Now the basic point of this set of positive semi-definite matrices that we want to use for defining semi-definite programming is that the dual of the set of positive semi-definite matrices, in the sense that we just defined, is the same set. This set is self-dual. That is, if I take the set of all positive semi-definite matrices for which the inner product with every single positive semi-definite matrix is non-negative, then I get again the set of positive semi-definite matrices. So why is that? So suppose I start out with two symmetric matrices x and y. So let's look at the second line here. So you want to recognize that the inner product of these two matrices, when you think about them as vectors in r to the n squared, that is, you just list out their entries, the inner product is just the trace of the matrix product of x and y. I hope that's clear from earlier calculations. Okay. So you can define this inner product basically by computing this trace. Now let's verify that this cone is self-dual. So suppose I have a matrix X which is symmetric but is not positive semi-definite. That means I can. I mean, also it's not. So it's certainly not zero then. So I can find a vector z, non-zero vector z, for which the quadratic form defined by this matrix is negative. So if X is symmetric but not positive semi-definite, I can find a non-zero vector z, so that z transpose xz is less than 0. Now you should know that the trace of matrices is invariant when I switch the order of multiplication of the matrices. So let me consider the matrix X. You can see where this hand is, the arrow on the screen. Take the matrix X, I multiply it by the matrix z transpose. You can think of it as multiplying three matrices: the matrix X, the vector z viewed as a column matrix, and the vector z transpose a row matrix. So I can just switch the order as I like. I can move the z transpose to the left, I'll get the same trace. This is just a number, so I don't even need to write a trace on it, and because of this property, that is negative. But z transpose is a positive semi-definite matrix. It's a rank 1 positive semi-definite matrix. So if X is not positive semi-definite, I have found a positive semi-definite matrix for which the inner product is negative, so X cannot be in the dual cone. Okay? Conclusion is that of this calculation is that if any matrix that is not positive semi-definite cannot be in the dual cone of the set of positive semi-definite matrices. Does that make sense? That's what this calculation does. Second calculation is the following. Suppose you give me a matrix X which is positive semi-definite. We know that we can diagonalize it. That is, we can find eigenvectors and non-negative eigenvalues so that matrix X can be written in this form. This basically is telling me that the eigenvalues are lambda I, and that the eigenvectors are ui, and the ui form, as you know from symmetric matrices, they form an orthogonal set, so orthogonal basis. So I write X like this, and I compute the inner product of X with any positive semi-definite matrix Y. So I'm computing the trace of X and Y. So let me spell out the trace here. I replace X by sum of lambda I ui transpose. I can change the order of these multiplications as I like. So I move the y between the ui and the ui transpose. And then I actually move the ui to the right. So I move the ui to the right, and this just gives me a bunch of numbers. So these are all non-negative because y is positive semi-definite. So I've concluded that this inner product is non-negative. So I've shown you that every single positive semi-definite matrix lies in the dual cone of the set of positive semi-definite matrices. Hope that made sense. So if you don't understand the details of the proofs, the slides will be with you, so you can check this at your own leisure. Let's just accept the conclusion. So what is the conclusion? Conclusion is that the set of positive semi-definite matrices viewed as a cone is self-dual. That is, its own dual. That's the conclusion. So now we're going to go into the real business. So we're going to define a class of optimization problems called semi-definite programs. And the way you want to think about the entire structure of the things that we are telling you in this course and that you will learn if you study optimization further on is that there are various classes of optimization problems. Linear programs are so to speak the smallest class. Every linear program is a special case of a quadratic program. Every quadratic program is a special case of a quadratically constrained quadratic program, which is a special case of an SOCP, which is a special case of an SDP. SDPs themselves are not really the most general class we're interested in. There's a class of so-called conic programs, which are even more general than SDPs. And then there's the most general class of convex programs, and further people even study nonlinear programs. Now, of course, people know a lot more about the simpler classes of problems, and if you want to study a problem in applications, you would want to try to identify the leftmost class in which it is, and then apply the relevant software for it. Okay, so this is a general picture of this field, and we are now going to define what semi-definite programs are. So for that, we need to define something called a linear matrix inequality. So let's walk through this slide. So now I'm considering just a set of symmetric matrices, Sn. Sn is a vector space. You should remember that. If you take any linear combination of two symmetric matrices with coefficients being either positive or negative, you'll end up getting a symmetric matrix. So it's a vector space. So what we're going to do is do the following funny thing. We are going to pick m plus 1 symmetric matrices. I index them by f0, f1 through f sub m. So each of these is a symmetric matrix. No assumptions about positive semi-definite or anything like that. And I'm going to define, I'm going to basically fix my f0. It's going to be something like a constant matrix. And then I'm going to allow myself to scale the matrices f1 through fm, each of which has got its own coefficient, x1 through xm. I'm going to consider the set of all matrices of this type that I can create as the coefficients range over all possibilities. So I've basically got a vector of coefficients which ranges over Rm. So I get a whole family of symmetric matrices. This forms what is called an affine subspace in the space of symmetric matrices. That is, except for the fact that I've got this non-zero f0 which moves things away from the origin, basically I'm defining a subspace in the space of symmetric matrices. Does that make sense? That geometric picture. Question?
And so the reason you know that it's a subspace is like that has a set of symmetric matrices is itself a vector space. So you know it's closed.
First of all, this is not a subspace. If the f0 was 0, then the resulting set would be a subspace of Sn. Because I can take any two, a linear combination of any such expressions can also be expressed in the same way. But this is what's called an affine subspace. An affine subspace is not a subspace. That's confusing terminology. Yeah, an affine subspace is a subspace moved by a constant. So if you want to think in two-dimensional space, you have a line going through the origin that would be a subspace. If you move that line so that it goes through some other point, that would be called an affine subspace.
But this f of x is itself a symmetric matrix.
Yes, each fx is a symmetric matrix. As you let x range over all possibilities, you get a set of symmetric matrices. That set turns out to be basically a subspace in Sn moved by some constant, namely f0, moved by the matrix f0. That's a geometric picture to have. So this affine subspace, so to speak, this is an instance of what's called a linear matrix pencil. This is terminology that you can look up. You'll have the slides. All these things people talk about a lot. You don't have to absorb every single thing that's on the slides instantly at this moment. Plus, you probably can't anyway, because a lot of it is very, very, there's a lot of information I'm throwing at you. Now, what is a linear matrix inequality? A linear matrix inequality is an inequality that has the following form. We are going to try to impose a constraint on the coefficients, x1 through xm. And the constraint we impose is that the symmetric matrix that we create in this way must be positive semi-definite. This constraint is either true or it's not true. Whenever it's true, we say that the linear matrix inequality is satisfied. Now, the set of all coefficients for which this linear matrix inequality is satisfied is the kind of set over which semi-definite programming operates. Okay, that's the key thing. Now, it's good to have pictures. I think my pictures are going to come later, or maybe I missed. I'm not sure what's going on. Okay, so yeah, I missed it. So let's see. So let me also state this. So let me first tell you what a semi-definite program is, and then we'll start to see some pictures. So what we're going to do now is we're going to try to optimize, minimize in general, or minimize same as maximize because you just need a negative sign. We're going to minimize a linear combination of the coefficients x1 through xm with some weights defined by the vector c, so minimizing some linear expression sum of ci xi, subject to the condition that the coefficients verify a linear matrix inequality. So this is how you define a semi-definite program in one of its key forms, which is called inequality form. Let's recap. You're given a m+1 symmetric matrices f0 through fm. f0 is special because it's like a constant term. The other fi's are being scaled by these coefficients. You're considering the set of all possible coefficients for which this expression turns out to be positive semi-definite, and over that set of coefficients you want to minimize some linear expression. So the data of the problem are the matrices f0 through fm and the coefficients of your cost function c, c1 through cm if you like. So you're trying to solve a problem like this. This turns out to be a convex problem because the set of coefficients that verify the linear matrix inequality turns out to be a convex set. So it's a special kind of convex programming problem, minimizing a linear function over a convex set. One interesting thing to observe is that instead of writing down a whole bunch of linear matrix inequalities, I can just write down a single linear matrix inequality, because if I have a matrix positive semi-definite and another matrix I wanted to be positive semi-definite, I can put them into a block structure and just require that entire block matrix is positive semi-definite. It's equivalent to requiring that each of the individual sub-blocks in the diagonal parts are positive semi-definite. In the definition of convex optimization problem earlier, you probably had it defined in terms of equalities and inequality functions, but now we are generalizing our notion by just thinking of it as an optimization problem over an arbitrary convex set. But in a semi-definite program, the criterion is also just linear. Okay. So now some pictures which might make some of this more interesting. So here's basically what's going on from a geometric point of view. So there is a cone. Okay, the picture is quite subtle. Okay, this picture is being drawn in the space of symmetric matrices, but the program itself, as I've defined it, is in the space of the coefficients xi. So this picture is not in that sense directly relevant to the program I wrote down, but it allows you to understand what's going on. So this cone here, the thing that looks like an ice cream cone, is a visualization of the set of positive semi-definite matrices as a subset of the set of all symmetric matrices. It's a cone in the space of symmetric matrices. The hyperplane, the affine subspace that I've drawn here, is a visualization of the linear matrix pencil. It's basically all expressions of the type f0 plus sum of xi fi that I can create as the vector x ranges over Rm, that is, as the coefficients range over all possibilities. Now, what it means to satisfy linear matrix inequality is basically it means to be inside the red set, because the red set is the intersection of the linear matrix pencil with the cone of positive semi-definite matrices. And basically, with the way we define the program, we are looking at the coefficients, those values of the coefficients x1 through xm, for which you lie inside the intersection. But it's clear that the coefficients are in one-to-one correspondence with points inside the intersection. So it doesn't matter whether you think of it in terms of the intersection itself or in terms of the coefficients that define a particular point inside the intersection. Now, there's a beautiful terminology. I don't know who came up with it, but whoever came up with it is a genius. So this set of coefficients is what's called a spectrahedron, and it's supposed to remind you of polyhedron. And the idea is that this is defined in terms of spectrum and so on, right? So that's why people call it a spectrahedron. Very beautiful word. And so in semi-definite program is basically a problem of minimizing a linear functional on a spectrahedron. Question? So the feasible set is the spectrahedron? The feasible set would be the spectrahedron, that's right. It would be a spectrahedron. The spectrahedron is a set of coefficients for which that the red set, if you like, in the space, or equivalently the space of coefficients that define the red set. Question? You also said that the coefficients Points in the red set, yeah.
Okay.
This picture is being drawn in the space R to the n cross n. Because my cone is lying inside that space,
right,
or in the space Sn if you like, which is a smaller space, and the linear matrix pencil is also in this space. But the way I defined my earlier program in the previous slide, I defined it in terms of the x's. So the x's are just the coefficients, the x1 through xm, that define the f of x.
How do you know some other combination of coefficients will achieve that same value?
Well, if you have a matrix that is defined in terms of f0, f1 through fm, in terms of these linear combinations, then if you have a specific set of x's, you'll get a specific point in here, right? If you have two, that's an assumption. Yeah, let's just leave it at that. Yeah, thank you. That's a good question. Yeah, let's just leave it at that. So at the level of generality that I've written down, it's what I said is not quite accurate. Yeah, but let's leave it at that. Thank you for pointing that out. Okay, so now I want to say, I might as well say this verbally, that some of these pictures are taken from some beautiful papers in the literature, and in the interest of fair use, since this is just for teaching, these pictures have been lifted here, but they're under copyright, so please don't use them or post them on the web or anything like that. So when we think about the program in the way I've written it earlier, we think of it in terms of the coefficients x, but this picture is in terms of the matrices f of x. Now, you're familiar with linear programs in inequality form. So in order to better understand SDP in inequality form, let's just do a comparison between the two of them. By the way, I've taught 1.5 hour lecture courses quite a lot, and I've learned that it's good to take a break. So at 1:25, we are going to have a 5-minute break. I learned that from Babak, who we all know is a great teacher. And the theory of that, which you might also know, is that there's something called your attention, which tends to decrease as time progresses. So if you have a break, then the attention resets. So even though you have a break, the integral under the attention graph is higher than if you don't have a break. This has actually been proved. People have done studies about this. So we'll have a 5-minute break at 1:25. Okay, so now let's look at this slide. This is a very interesting slide because it connects with things that you already know. On the left-hand side, I've got linear programs in inequality form. On the right-hand side, I have the semi-definite programs in inequality form, which we just defined. In a linear program in inequality form, you're minimizing a weighted linear combination of the variables, which is what you're doing also in the semi-definite program. The constraint in a linear program, though, is that in inequality form is that some inequalities need to be satisfied of this sort. Here our constraint is that some matrix needs to be positive semi-definite. We just discussed the right-hand side. We said that there is a cone in the space of symmetric matrices, which is the cone of positive semi-definite matrices, and we are considering the intersection of a matrix pencil with the cone. It turns out that the linear program can also be visualized in exactly the same way. What you have is a cone in the set of k-dimensional vectors, which is the cone of vectors with non-negative coefficients. It's easy to see that that's a cone. It's basically the positive orthant or the non-negative orthant in k-dimensional Euclidean space. Then you're looking at a subspace, which is defined by B, which is this vector, minus all possible linear combinations of the columns of the A matrix. So F1 through Fm are the columns of A. And you want B minus A times x to be bigger than or equal to 0 coordinate-wise. So you basically want it to intersect this cone. So you can think about a linear program in exactly the same way. The set over which you're doing the optimization is the intersection of a cone with an affine subspace. It's the exact same mental picture. So that's what we are doing here. There's another form in which the SDPs show up, which is analogous to the way in which linear programs have another form, which we call the standard form. In this form, the variables are actually more akin to what I had in that earlier picture, which is that they are the coefficients of the symmetric matrix itself. So now the variables are the coefficients of a symmetric matrix. The minimization is over a symmetric matrix. We are minimizing a linear combination of those coefficients, which is basically a trace. So we are taking a trace of C times x. So C defines the coefficients, because remember that the trace of Cx is sum of Cij xij. So we're trying to minimize this linear combination, subject to certain trace conditions being trace equalities and a positive semi-definiteness condition on our variables. So this is called the standard form. We'll say more about it as we go ahead. But basically this is analogous to the standard form for linear programs, and this slide illustrates that. So remember, you're going to have these slides, you can check everything. If you find any typos, let me know. So you can take your own time to understand this if you wish to understand this material. So in the linear program in standard form looks like this. Again, we have some linear weighted linear combination of the variables that we try to minimize, subject to some equality constraints, and the variables being non-negative. Analog of the variables being non-negative is that the matrix of variables is positive semi-definite. The analog of these equality constraints is that certain trace equality constraints hold, and the objective is again to minimize an inner product. So this is the analogy. Okay? It's just that it's sort of similar to things that you've seen before. Now let's see some interesting pictures. So this has beautiful papers on this subject written in the notices of the American Mathematical Society, in which have all these lovely pictures. So let's look at some examples of a spectrahedra. So here is a cylinder, and a cylinder is an example of a spectrahedron. A cylinder can be defined as the set, cylinder is in 3 dimensions, and it's a set of all coefficients. So the z goes vertically, and x and y are in the horizontal plane. Cylinder is a set where x squared plus y squared is less than or equal to 1, this particular cylinder, and z lies between -1 and 1. These conditions can be expressed basically in terms of a spectrahedral kind of inequality, the linear matrix inequality. You take F0 to be the identity matrix, take F1 to be this matrix, that is 1 and -1 on the diagonal, everything else 0. F2 to be this matrix, there's only 2 places which are 1, everything else is 0. F3 to be this matrix. Your coefficients are x, y, and z. When you form the corresponding weighted linear combination, you get the matrix up here. So you get 1 plus x, 1 minus x, y, y, etc. You can just match this for yourself. What is the condition for this to be positive semi-definite? Well, the diagonal 1 plus z has to be bigger than or equal to 0, which is z less than or equal to, which is basically says that z is bigger than or equal to -1. 1 minus z bigger than or equal to 0 says that z is less than or equal to 1. And this 2 by 2 block being positive semi-definite basically says that 1 minus x squared is bigger than or equal to y squared. Yeah. So you could write this this fixed single linear matrix inequality as, say, 3 different linear matrix inequalities if you like to, if you wanted to. You could take one for the 2 by 2 top block, one for this guy, one for that guy, up to you.
Okay.
Yeah. That connects to what I said earlier. Thank you. So in any case, so this tells you that you can now do optimization of linear functionals over a cylinder, which is something, which is not, I mean, of course, you could have defined it earlier as a general convex program, but this is an example of kind of things that show up as spectrahedra. Now, there's a very beautiful analogy between polyhedra and spectrahedra. So polyhedron is defined in terms of, some linear hyperplane type inequalities. So you have to satisfy some linear inequality constraints. You take the intersection of that. So on the left, you have a typical picture of a polyhedron. All these figures are lifted from these papers in the notices of the AMS. And on the right, I have a spectrahedron. Now, when you think about a polyhedron, you can think about, if you want to think about it geometrically, you have this mental picture that it has some facets and faces, right? You keep taking some lower dimensional objects as you have more and more of these inequalities become equalities. You can think about spectrahedra in exactly the same way. So let's try to just illustrate that through the cylinder example. So here is a rank analysis of the cylinder. So basically, if any one of these conditions, x squared plus y squared equal to 1, which is a boundary condition, or z equals 1 or z equals -1 gets satisfied, exactly one of these conditions gets satisfied, then you've basically dropped the rank by 1, and that is like being on one of the, so to speak, faces here. So either you're on the top disk or the bottom disk, or you're on the thing that is, the boundary that is that looks like a strip. If 2 of these conditions hold, then you're either at this top circle or at the bottom circle, and all 3 of the conditions cannot simultaneously hold. So you can think about spectrahedra analyzed by rank hierarchically, just like polyhedra. It's a very, very analogous theory. Here is another very important spectrahedron. It's called the elliptope. This is what you can visualize it. It's a set in 3 dimensions. So it has coefficients x, y, and z. It's basically the set of all x, y, and z for which this matrix is positive semi-definite. This matrix can be thought of as being created from F0, which is the identity. This is F1, this is F2, this is F3. And if you think about it, this turns out to be actually the set of all vectors of the type cosine alpha, cosine beta, cosine gamma, where alpha, beta, gamma are pairwise angles between 3 unit length vectors in R3. You can understand that by realizing that any 3 by 3 matrix, symmetric matrix, if it's positive semi-definite and it has 1s along the diagonal, that is equivalent to it being expressible as U transpose U, where U is a matrix which has got columns of norm 1. So I mean, you can basically just try to write down, diagonalize this matrix if you like, and this you'll end up seeing this, and the U's have to have norm 1 columns because the diagonal entries are 1. So this you can think of basically, you can think basically of these 3 vectors that you pick up coming from this matrix U, because all of its columns have got length 1, so they're like 3 length 1 vectors, and there are certain angles between these 3 vectors, pairwise angles. You take the cosines of those angles, this is basically the object that you get. So this is related to the study of correlation matrices and probability theory. So very, very important applications coming from all these ideas. Here is another example of a spectrahedron. This is picked up actually from your book of Color Theory and El Ghawi, which you use as one of the books for this course. So here I just picked f of x to be this linear matrix pencil. The condition for the coefficients x1 and x2, there are only 2 coefficients here, it's a 2-dimensional picture. The conditions on them for this matrix to be positive semi-definite can be figured out by looking at all the principal minors of this matrix. So they turn out to be a bunch of algebraic conditions. I wrote down all of them here. So 3 conditions coming from the diagonal entries, conditions coming from the 2 by 2 blocks, and conditions coming from the from the full matrix. And that defines this weird looking set that looks a bit like an Easter egg which has been slightly deformed, and that's a set which is convex. It's a spectrahedron. You can do optimization over sets like this. Amazing subject. So you can basically all kinds of interesting algebraic problems that show up in applications which happen to fall within this class of problems can be studied. Very, very important subject. It's studied a lot. And here I use the fact that a test for positive semi-definites, all the principal minors are non-negative. So principal minors here, there are basically 3 of them. I mean 3 plus 3 plus 1, sorry, so 7 of them. And here's a couple of nice pictures also. Here's a spectrahedron that is in 3 dimensions defined in terms of this matrix pencil. It's called the pillow. Here's another spectrahedron defined in terms of this matrix. This thing looks a bit like a Hershey chocolate thing, right? So I don't know what it's called anyway. Question?
Sorry for a silly question, but what are the principal minors? Are they the anti-diagonals?
Principal minors, yeah, they're things that go along the diagonal. So in this example, you basically would take the 1, 1, 2, 2, 2, 3, then you take the 1, 2, the 2, 3, and the 1, 3, and then the full guy. That is, you don't get off the diagonal. You don't take something like A1, 2, A1, 3, A2, 2, A2, 3. That's the definition. Again, you can look it up. Yeah. I hope that made sense. Yeah, that's okay. So now we want to say some things about how this connects to what we know, and I'm getting close to the break point. Let me just run through these. So every linear program can be expressed as a semi-definite program, because the condition that A transpose X less than or equal to B can be written as a linear matrix inequality by just taking matrices as scalars, right? So I take my f0 to be b. B is just B is a real number, let's say. So f0 is just a scalar. Fi I take to be a sub I, that is the ith entry of the matrix of the vector A. So these are just scalars, and I think of this A transpose X less than or equal to B as basically B minus A1 x1 minus A2 x2 blah blah bigger than or equal to 0, and that's a linear matrix inequality. So I can just write a linear program using this. That's easy. Now there's something you need to know called the Schur complement rule. I don't know if it's been done in class. Sometimes we do it in a homework problem or something. Have you seen the Schur complement rule for positive semi-definiteness? Okay. So this slide tells you what the Schur complement rule is. We don't need to walk through the proofs. It might take too long. So let's say that you've got a matrix, a symmetric matrix M, which is n plus m times n plus m matrix, and it's written in blocks. So A is an n by n block, B is an m by m block, and it's symmetric. So if I have an x here, it better be an x transpose there. Suppose we have a symmetric matrix. I assume that A is for this version of the Schur complement rule, I assume that A is a positive definite matrix. So again, the notation of positive definite puts 2 pluses in the subscript. So S sup n and then 2 pluses means A is positive definite. Basically, the Schur complement rule tells us a way of figuring out whether M is positive definite or positive semi-definite. So the result is that M, the whole matrix M, is positive semi-definite under the condition that A is positive definite if and only if this expression is positive semi-definite. What is this expression? I take B minus x transpose A inverse x. So A has an inverse because it's assumed to be positive definite. So B is m by m, X transpose is m by n, A inverse is n by n, and X is n by m. So this is an m by m matrix, which is of course symmetric, and the statement is that m is positive semi-definite if and only if this part is positive semi-definite. Similarly, m is positive definite if and only if this is positive definite. This is the Schur complement rule due to somebody called Isaiah Schur, and there's a two-line proof which is here, but we won't go through it. So before taking our break, let me just walk through the next couple of things I want to say. So I can write quadratic programs as semi-definite programs. Quadratic program is something where the criterion is a quadratic function plus some linear part, right? Basic general quadratic function, maybe with a constant. We always ignore the constant, subject to some linear inequalities. So the P is supposed to be positive, is a positive semi-definite matrix. I write it as W transpose, and then I can use the Schur complement rule to write this program exactly as this program, which is a semi-definite program. What I'm doing here is I'm making the constraints gx less than or equal to h constraints into linear matrix inequality constraints, just like I did for the linear program. But in order to deal with this nonlinear objective function, the objective function is quadratic, I introduce a dummy variable for this x transpose px. It's playing, that is what t is playing the role of that. So I use one more variable, auxiliary variable. I put in t there, but I insist that t should satisfy this matrix inequality. The Schur complement rule tells me that because the Schur complement of this identity is this expression, I get this positive semi-definite inequality precisely when x transpose w transpose, there's a transpose missing, I'm sorry, I already screwed up. So there should be x transpose, maybe w transpose wx is this thing. So this expression is positive semi-definite. So this is essentially boils down to, since if w transpose is p, then this boils down to requiring that it ends up that I'm basically minimizing the same thing, because I can push this t all the way up to x transpose px. That's the idea. You get? I hope you got the scheme of it. Okay, don't hold me on to the complete details, because we don't have the time to go through all that. This is how this explains how QP can be modified into SDP. So there seems to be some typo here. I'll fix it before posting the slides. You can do the same thing for QC QP. You have a quadratic objective and you have a bunch of quadratic inequality constraints. You replace each of these positive semi-definite matrices by some transposed object like this, and use the Schur complement rule to convert that into an SDP type constraint. And you can do the same thing for SOCP, where this kind of constraint which shows up in SOCP, if you remember SOCP, you get constraints like this. Those can also be converted into positive semi-definiteness type constraints, which are also basically coming from the Schur complement rule. I'll just leave it at that, because the goal is not to walk you through every single detail, but just tell you some lay of the land for this subject. So you can walk through these slides and check every single statement. Of course, there was some typo there. So these are ways of showing you that all these earlier classes of problems that you studied are special cases of SDP. So now let's take our break, and I'm going to then try to tell you, we're going to have about 20 minutes after the break. So I'm going to just tell you something about SDP duality. The form, so we know that if you have a linear program in inequality form, you can write its dual in standard form and vice versa. Same thing in SDP. You can write the dual of an SDP in inequality form as an SDP in standard form. The dual of an SDP in standard form as an SDP in inequality form. I'll just show you how that goes. It's all algebra. Got to check a lot of details to make sure it works. Yeah, I'm going to explain that also to you. Yeah, same as an LP. Yeah, by just redoing the variables. Very good question. Yeah. So that's the slides on that also. And then hopefully in the last 10 minutes or so, I'll give you a couple of applications of this business. One of the major applications is in computer science. Some of you may have heard about the Gomans-Williamson result, which is one of the major things that set off a lot of theory and approximation of algorithms. I'm hoping to explain that to you also. So let's take our break now, back in 5 minutes. So I just quickly ran you through, at least just showed you the slides for how you might convert, say, QP, LP, QP, here's the LP1, QP, shows you how to write a QP basically as an SDP. So given the variables in a QP, you use the same variables with an auxiliary variable t, and you convert the coefficients p, q, g, h accordingly into some coefficients in the SDP. Same sort of thing for QC QP. You've got to introduce some auxiliary variables t0 and a bunch of auxiliary variables ti, and do some conversion. it takes some time to check all this carefully, so you better do that offline if you're interested in this. The slides, I believe, are correct. And SOCP can be converted similarly into SDP. So now let's discuss SDP duality. So suppose that the primal is in standard form. So standard form, remember, standard form SDP is something where the variables themselves are entries of a symmetric matrix, and the objective is linear, so it's a trace of C is a bunch of coefficients, matrix of coefficients. So you want this trace to be minimized, subject to this matrix X satisfying some linear conditions. So there are some AI matrices, trace of AI X is some number BI, and the matrix X has to be positive semi-definite. So it turns out that you can dualize this problem, and it leads to something, but the right way to dualize it is to do something called the conic dual. And the conic dual is connected with the dual cone story that I discussed earlier. And if you do the duality, then you find the dual problem looks like this. There are some dual variables which are called nu, which are denoted by nu. There's going to be m of them. M is equal to the number of constraints here. So it's consistent with the general duality story that you see, right? One dual variable for each constraint. And there's going to be some positive definiteness inequality. That's what's going to happen. So let's see how that works with conic duality. So the key observation here is the fact that the cone of positive semi-definite matrices is self-dual. That's why I spent some time discussing that at the beginning. So one way to express that fact is the following: that if you consider a fixed symmetric matrix X, and you let Z range over the positive semi-definite symmetric matrices of the same size, and you try to maximize minus the trace of Z times X. Trace of Z times X, remember, is sum of Zij Xij, summed over Ij. You try to maximize the negative of that inner product. If X is positive semi-definite, you will get 0. Because Z being positive semi-definite is only allowed to range over positive semi-definite matrices, so the trace of Z times X will always be non-negative. So you're trying to maximize its negative. The best you can do is make Z equal to 0. So you'll get 0. On the other hand, if X is not positive semi-definite, you'll be able to find some direction to move, so to speak, in the Z space so that you make this equal to infinity, because you'll be able to make it as negative as you like. This is sort of equivalent. If you remember how the duality works, right, the basic idea, Lagrange's great idea, is to replace these inequality constraints or equality constraints by somehow thinking of them as introducing dual variables that basically makes you infinity if you're not satisfying the constraint, or 0 if you're satisfying it. Same kind of idea here. So the statement is equivalent to the statement that this cone is self-dual. And we'll be using this property, and so now we can see how the duality looks like. It's a long slide. Again, I'm not going to go through every single line carefully, and if you want to understand it, you're going to have to go through it yourself. I'm just going to sketch for you how it works. So we've got, remember, the problem itself is to minimize the trace subject to some equality constraints, Bi equals trace of Ai X, and subject to X being positive semi-definite. So we dualize the equality constraints by dual variables nu I, just like we do in all the linear programming business that you have. We dualize the positive semi-definiteness constraint on X by introducing a dual matrix Z and treating the trace of Zx as the sort of dualizing object. The idea being that if X is positive semi-definite, when you try to maximize minus the trace, you'll end up getting 0. Otherwise you'll get infinity. So it's like a test for seeing whether X is positive semi-definite or not. That's basically what you do when you do the dualization, right? Suppose you look at nu times some fixed number X, and you try to vary nu, right? You'll be able to push things to minus infinity unless the nu is 0. I mean, unless the X is 0, so to speak. So that's basically the way. So it serves as a kind of a test for deciding that X is 0. That's how the dual objects work. No, so the way I've set up the Z, it's not immediately apparent how this corresponds to the same picture. But you could dualize in many different ways. I mean, that's one thing to realize in optimization, is that duality is a very freestanding kind of idea. So if you want, you can dualize based on interpreting positive semi-definiteness in terms of the principal minors, and introduce variables that verify that each of those principal minors is positive definite. It might give you a different dual. But here it's not that apparent because the Z's are doing things coordinate by coordinate. So it's not clear how these dual variables that are represented in the coefficients in the Z connect to dual variables that are related to the principal minors.
Okay,
But you can duality is an extremely free concept, which helps, and you can a lot of inventiveness involved in finding the right duals and so on. Just a way of trying to specify whether condition holds or not in terms of some dual object. And that's what in this case we're doing what's called conic duality. So we're specifying that X is positive definite through this dual object, which is a Z matrix, and the trace of ZX is like the thing that verifies for us whether X is positive or not. So we had this minimization problem. We have converted it into a min-max problem. The reason we managed to do that is if you just drop the min, just think about the max. When you take the max over nu, you're basically going to end up, you're trying to minimize the max. The max is going to run off to infinity unless the bi equals the trace of AIX. And the max over Z is going to run off to infinity unless the X is positive semi-definite. So this is just another way of writing that original minimization problem subject to constraints, the min-max problem. The dual problem will be a max-min problem. So you do interchange the max and the mins. Now you try to figure out, fix the nus and the z's, and you try to maximize what is inside over X. You see that X is hitting C minus Z minus the sum of nu I AI, that is this expression here, and you're forming a trace. So when you try to do the min over there and you're trying to maximize eventually, you basically want this expression to be 0. Otherwise, because it's coordinate by coordinate multiplication, otherwise you'll be able to, X ranges are all symmetric matrices. So otherwise you'll be able to, so to speak, fool the max by forcing the min to be minus infinity. So it ends up giving you an equality constraint. And what is left is the sum of nu I bi. So this is what it looks like. Now Z was supposed to be positive semi-definite, so this being equal is equivalent to saying that this difference is positive semi-definite, and there is my inequality form. Okay? Go through the calculation carefully, but this is the idea. Now same sort of thing. If you have a primal and inequality form which looks like this, and you do a conic dual on it, you'll end up getting a dual in basically standard form. And the primal is defined in terms of this F0 through F0, F1 through Fm, which define a linear matrix pencil, and the coefficient C, the weights that define the objective. And then the dual will also be defined in terms of those very same objects, of course. But this is what it looks like. And here, of course, the variables are now matrix variables ranging over the set of symmetric matrices. And the objective is defined by the F0, and they've got some traces. So play the same game. So now you write the primal as a min-max problem. And in the primal, we have the objective is C transpose X. You wanted this expression, F0 plus this linear matrix pencil expression, to be positive semi-definite. So you introduce a dual variable that serves as a witness for that constraint. And when you do the max, you notice that only when this is positive semi-definite will it make sense from the point of view of the minimum. Otherwise, things will run off to infinity. The dual, you interchange the max and the min. So now let's fix the Z. Let's minimize this over the X. So when you minimize this over the X is completely free. So you basically want these things to be 0. So that becomes a bunch of equality constraints. And the objective becomes this trace. And the Z was anyway required to be positive semi-definite. That's a duality. Okay? So this is how you sort of connect the duality in SDP. Now you raise the question of how to convert standard form into inequality form. So that's a bunch of algebra. If you have something in standard form, you introduce some basic matrices which are denoted here in red. So EII is a rectangular matrix, is a square matrix which has got 1 in the II location. It's supposed to be symmetric matrices, so it's already symmetric because it's diagonal. EIJ, because it's supposed to be symmetric matrices, it has got 1 both in the IJ location and in the JI location. So this is just some notation. And I'm going to introduce some variables xii for the diagonal ith entry and xij for the off diagonal ij entry, but it's playing the role symmetrically, so it covers both ij and ji. So in terms of these variables xii and xij, I can rewrite my objective as this expression, because this trace basically works out to this, and the equality constraints become this. You can just check that. There is one such equality constraint for each u going from 1 through m. And then, of course, I have the positive semi-definiteness constraint on the X. So this is just starting things off. And now I have the standard form rewritten like this. But I can rewrite these are just baby equality constraints. I can rewrite them as if they were linear matrix pencil constraints. Because they're just scalar stuff, I can introduce some, using my capital E matrices, I can just write that as a positive semi-definiteness constraint on something. And so here are my equalities. So these equalities are now interpreted basically as two inequalities, and each of those inequalities, inequality is basically both less than equal to and bigger than equal to, and the bigger than equal to you can deal with by putting a minus sign, or the less than equal to, whatever. So you just convert those into linear matrix inequalities. Here you already have a linear matrix inequality which corresponds to the positive semi-definiteness condition on the x. So you can club all these things by putting them in some giant block structure, and that becomes your inequality form. You can check the details, but this is this mechanics of how you go through this. And same sort of story going from standard form to inequality form. So suppose you already are in standard form. X is allowed to be free, so you split it up into the positive part and the negative part. For this positive definiteness condition, you introduce a slack matrix which represents the gap between this matrix f of x and the 0. So the first step is to write this as the objective you write by separating out the positive part of the variables and the negative part of the variables. So x is basically x plus minus x minus. So I substitute that, I get C transpose x plus minus C transpose x minus. And for these things I write them as equality constraints by introducing the slack variable. The positive part has to have non-negativity constraints, the negative part is non-negativity constraints, and the slack variable has to be positive semi-definite. So this is the first preliminary massage of the inequality form SDP. And then I rewrite that by introducing some giant matrices. So I put all the entries of my x plus part along the diagonal, the entries of the x minus part along the diagonal, the slack variable as a block here. So this is a big 3 by 3 block. The coefficients I sort of put in a similar block so that I get the correct objective. And then I create certain matrices which are going to allow me to put things into the standard form for SDP. So if you go through the algebra, you'll find out that what I wrote earlier turns out to be this expression, where you have essentially some equality constraints at the trace level. You want certain structure to the overall matrix that I'm dealing with, because I want to only solve problems where the x has got just diagonal entries and everything off diagonal is 0, except for the slack part, which is allowed to be completely free. So I introduce a bunch of constraints that force all those off diagonal entries to be 0, except for the slack part, except for the bottom block, because that block is supposed to represent the slack variable, so it can have both diagonal and non-diagonal and off diagonal entries. It's too fast for you to understand the details, don't worry. That was not the point. If you go through the slides, you'll be able to check every single thing that's on the slides. Okay? Just a general picture of how to do the algebraic manipulations to end up getting it into the other form. And it's also important to know that strong duality can fail in SDP, even when the primal and the dual are feasible. So you might have been told, I don't know whether you were told this in this course, that in linear programs you always have strong duality unless both the primal and the dual are not feasible. That's an example like that. In SDP, strong duality can fail even when the primal and the dual are feasible. And here's an example. Again, not possible to go through the details of that example. We don't have time, not that it's not possible, we could go through it, but I want to say some more interesting things. So we've got about 10 minutes to go. So let's try to say some more interesting things. It's a good point to stop and ask if there are any other questions, because I'm going to move on to do a couple of examples. Yeah, you would be able to massage it into an SOCP. The duality in SDP is consistent with the duality that you were told about in SOCP. Yeah. It may not look apparent to you that it is one, but if you'll be able to massage it, so that it looks like one. Yeah. Okay, so now I'm going to tell you like a super famous result in computer science, which some of you might have seen before. And this is an approximation algorithm for the max cut problem based on semi-definite programming. This is a very, very old result already, but it has set off an enormous stream of work. And there's many, many people in computer science algorithms are studying it. One of the greatest experts is one of our own colleagues, Prasad Raghavendra, who's in the CS faculty. So people are trying to understand the role of semi-definite programs in complexity theory, and there are many, many results. So the max cut problem is a problem of where you have a weighted graph, undirected weighted graph. So graph is basically comprised of nodes and edges, and each edge has got some weight, so it's like some number associated to it. But you don't have to think of it as being positive, but if you want, you can add the same constant to all the edges and it'll become positive. So what you want to do is you want to create a cut in the graph. So you separate out the vertices into two pieces, set S and its complement V minus S. And there'll be certain edges that go across the cut, and you want to add the weight of all those edges, and you want to try to find a cut so that is maximum, that weight is maximum. It's called the max cut problem. You probably know about it. You might have even seen Gormans-Williamson stuff. So it's a very hard problem to understand, but it turns out you can approximate it very well, and the best known approximation to this day is the one that is based on an idea of Gormans and Williamson, which basically relates this problem to semi-definite programming. So I'm going to try to explain that to you. So first, let's formulate the max cut problem as an optimization problem. You can formulate it basically as a very baby-looking optimization problem. The objective is simply some quadratic form. W is a symmetric matrix defined in terms of the edge weights. So I mean, in my graph, let me assume there are no self loops, so all the diagonal entries will be 0, and every edge ij shows up as both, ij and ji, if you like, whatever. So you can think of W as some symmetric matrix. So the constraint is that the x's are got to be either +1 or -1. X equal to +1, xi equal to +1 means that it is on one side of the cut. Xi equals -1 means that it's on the other side of the cut. If you look at the last line here in red, if you compute this quadratic form, sum of xi, wij, xj, where wij are the eij or eij over 2, you can do the algebra. Essentially what ends up happening is that if I and j are on the same side of the cut, then they have the same sign. They're either both +1 or they're both -1. So their product is 1. And they introduce the corresponding edge cost with a positive coefficient, right? If they are on opposite sides of the cut, they introduce the edge cost with a negative coefficient. Is that clear? So you can do some algebra and figure out that this product basically is equivalently telling you about the weight of the edges that go across the cut. But if the guys that go across the cut with a negative sign, you just add them in twice to become a positive sign. So you end up getting 4 times the sum over the edge weights basically is this object. So you're trying to maximize the weight across the cut. So you're basically trying to minimize this quadratic form. This term is a constant which you don't care about. That's right. Yeah, exactly. So you're basically minimizing this quadratic form is equivalent to maximize the max cut problem. Now, the real difficulty of the max cut problem is that the constraints are that the xi have to be plus or minus 1. It's a combinatorial optimization problem. You can write it as x squared I equal to 1 for each I, but that's not a convex set. It just defines a 2-point set. So that's the real difficulty. So now the idea in the Gorman-Williamson's approach is first to dualize this problem using traditional duality. I don't know if it was told to you in this class, but you don't have to start with a convex problem to go through the Lagrangian approach to duality. You'll end up getting a convex problem, and then when you dualize it back, you'll get another problem which is not the original problem, but is some kind of natural convex version of it, convex relaxation of it. So the idea in this Gorman-Williamson approach is to start with this primal problem and just dualize it in the traditional way. So what does it mean to dualize it in the traditional way? You introduce Lagrange multipliers for the equality constraints. There are n of them, right? 1 for each vertex. So you're going to have n dual variables nu i. Nu i will be free variables because these are equality constraints. So you got the usual min-max business, and this is min problem because the early problem is a max problem, but we saw that this is a min problem. So you have a min-max thing, and then you look at the max-min version. So for each fixed choice of the nus, you're going to try to minimize this expression, which is basically the Lagrangian, because this nu I xi squared is like diagonal nu I being hit by x transpose x. And you see that this expression, when you do the minimum over x, you're going to get minus infinity unless this matrix is positive semi-definite. And when this matrix is positive semi-definite, then you want to push the x down to 0, and then you're left with basically this is the row vector of 1s hitting nu. So this is my dual. And this dual, you should look at it, hey, it looks a bit like an SDP, right? I mean, the point is, there's a positive semi-definite condition and a linear constraint, right? So this is an SDP in inequality form. Make sense? So now what you do is you dualize this dual, but using the conic duality for the SDP. So when you go through that process, this is now an SDP, and when you dualize that as an SDP, you'll end up getting a standard form SDP. So this is the SDP dual of the dual of our original combinatorial problem. And you can work through the algebra. It basically looks like this. So the constraint now is that you're doing it over a matrix of symmetric matrix of variables, and your W is the data of the problem coming from the weights on the edges, trying to minimize this trace, subject to the ZII being equal to 1 and the Z being positive semi-definite. So this ZI equal to 1 basically comes to the fact that the coefficients here are 1. And this basically ends up giving you upper bounds for the original max cut problem via the SDP. Because you have dualized the dual, whatever you can get in this problem is going to be something that is going to be an upper bound for what you can get in the earlier problem. I mean, when you solve this problem, because it's somehow a relaxed version of the original problem. So the minimum in the original problem will be basically you get the minimum in the original problem will be lower bounded here. So the max, I think, in the original case will be upper bounded. You can work through that. So anyway, we are left now with this SDP. So what is the idea here? So you solve this SDP. SDP can be solved. There are efficient algorithms solving this SDP. Now the solution to the SDP is just going to give you a symmetric matrix as a solution. So what you do is you pick a vector uniformly at random, and so you write the solution here. The solution is going to be a positive semi-definite matrix which has got all its diagonal entries equal to 1. So you can write it as U transpose U, where the columns of U are of norm 1. So essentially you can think of the solution as giving you n vectors in Rn. And if you think about the geometry of what's going on, then in effect what is happening is that the question of whether the xi, the signs the xi are plus or minus 1 is being replaced by the question of by the idea of trying to find an n-dimensional vector for each of the vertices of the graph. So you have relaxed the plus minus 1 condition to just finding a vector in Rn. This is a warning that I give myself when I have 2 minutes left. So that's where we are. We still have 2 minutes. Okay. So going through this relaxation allows you to associate essentially to every vertex a vector, and now the idea is you pick a random a vector which is a unit vector because the diagonal entries were 1. So you pick a random unit vector, and then you take the inner product of that random unit vector with each of these column vectors of the matrix U, which is where U transpose U equals Z, which you found from solving your SDP. And if that inner product is positive, you decide it's a plus 1. If it's negative, you decide it's a minus 1. That's a way to approximate the original cut. This is the Gormans-Williamson's idea. So when you do this, you can analyze it. It's running out of time. So you can basically find the probability that this vector gives you the two such U's lie in different sides of the cut, and for a randomly chosen vector. And that probability turns out to depend on the angle between the two vectors U and U prime. A simple calculation shows that it's 1 over pi times the arc cosine of U transpose U prime. So you're just picking this vector at random. In this picture, R is the projection of this randomly picked vector onto the two-dimensional subspace spanned by the U and the U prime. So when you go through this calculation and you find a lower bound for the arc cosine in terms of a linear expression in the angle, then you can essentially conclude that you get a lower bound which is this coefficient times what you would hope to get in the original problem, and this gives you an approximation factor which is still the best approximation factor for max cut. Since I've run out of time, I'm just quickly going through this slide. You can read this more carefully. And I won't go to the next example. I also have 2 or 3 slides here. Let's see, how many slides do I have? I have 4, 5, 6. Yeah, 6 slides here connecting with a problem of stability in control theory, which I don't want to abuse you, so I won't talk about it. I also have alarms here which tell me when to shut up, and you can just read it because the slides will be provided. So this is just this is last week anyway. I assume none of this is on the exam or anything. Just to give you some flavor of where things go from here. It's an incredibly important subject. These are just applications in computer science, but SDP is used all over the place. Many software packages. You'll encounter this in many application areas. So assuming that you continue to do something technical with your life, you might encounter this later on. Thank you.